Well, here's our video on solutions. And when you talk about solutions, the one molecule that you have to talk about is water. So here we have a water molecule, and we have a big oxygen atom bonded covalently to two hydrogen atoms. Okay, so there's the oxygen, and there are the hydrogens. Now, in this bonding, you end up with a lone pair of electrons that are around the oxygen, and what that does is push the hydrogens now down so that this is a V-shaped molecule. And because of that, water becomes a polar molecule that has a negative end and a positive end. Okay, and again, we call this a polar molecule. And because water is bonded like this, it dissolves polar substances like sodium chloride or common table salt. And common table salt is also a polar molecule, so we get the expression like dissolves like. So water, being a polar molecule, will dissolve polar substances, but it does not dissolve nonpolar substances like oils, butters, things that are nonpolar. Nonpolar solvents dissolve nonpolar molecules. So like dissolves like. When we're talking about dissolving, we look at solubility charts, and this common solubility chart has compounds on it, and it shows the solubility graphed for temperature. So let's look at KNO3. Just isolate this line for KNO3. Now this line is where saturation is. So if you have data that you're trying to look and how much KNO3 dissolves in water, then and you want a saturated solution, you're going to look directly at this line. So if you're plotting, say, if your 100 grams of water, say, is at 30 degrees Celsius, then we follow the line up and we see to have a saturated solution, it's going to be about 47 or 48 grams that you're going to dissolve to have saturated solution. But at this 30 degrees Celsius, let's say we have 60 grams that we're going to put in. Okay, if it falls above the line, anywhere above the line, then we say that the solution is super saturated. And if it falls below the line, like if we're looking at 30 degrees and we only have 10 grams, okay, that's right here in relation to the line. It falls below the line. So anywhere below the line is going to be unsaturated. Okay, so let's look at 50 degrees. What would we need to have a saturated solution at 50 degrees Celsius? Where we're going to follow the 50 degrees Celsius line up until it hits KNO3, and we're talking specifically about KNO3. It's going to be different for different compounds, but just for potassium nitrate, when we hit that line, we're going to travel to the left, and we're going to see that in 100 grams of water, we're going to have 80 grams that we can dissolve in that. Okay, 80 grams per 100 grams of water. But what if we had 300 grams of water? Well, if 80 grams dissolves in 100, 300 grams of water is 3 times this amount. So we'll just simply take our 80 and multiply it by 3 to get 240 grams. Okay, but what if we only had 50 grams of water? Well, 50 grams of water is half of 100 grams. So we're going to take half of our 80. So only 40 grams would dissolve in 50 grams of water. Okay, now when these things dissolve in water, they dissociate into ions in the solution, and this solution conducts electricity if it has ions in it. That's what you call an electrolyte. But what if they don't dissociate? What if they don't dissolve in water? Because some things don't. Well, then they form what we call a precipitate. That's a solid that forms in a solution because the compound is insoluble. So now the question is, well, how do we know if it does dissolve or doesn't dissolve? Well, that's why we have the general solubility guidelines. And here are some guidelines that tell you if something does dissolve or if it doesn't dissolve. So how do we use these guidelines? Well, let's look at this reaction here. We have silver phosphate. Okay, that's in an aqueous solution. So let's see if silver phosphate is soluble or insoluble. And what we do is we look for either silver or phosphate in these guidelines. So as we're reading these guidelines, we can see that on number 5, most carbonates, phosphates, and silicates are insoluble except for sodium, potassium, and ammonium. We do see silver, but that's in relation to chlorides, the exception for chlorides being soluble. So phosphates are insoluble. So silver phosphate would be insoluble. Now let's look at magnesium chloride. Okay, number 3, most chlorides are soluble except for silver, mercury, and lead. Well, this is silver, mercury, lead, so the magnesium would be soluble. So it is an electrolyte solution because the magnesium chloride dissociates, it's soluble. So we have an electrolyte solution, but it does have a precipitate in it. So when we mix these together, it goes through a double replacement reaction, and now we're going to get silver chloride and magnesium phosphate. They're going to switch partners. So let's look at our guidelines to see if any of this is insoluble. Well, number 3, silver chloride, it says chlorides are soluble except for silver. Okay, so this is silver chloride, so that's going to be insoluble. And our magnesium phosphate, that would be number 5. Most phosphates and carbonates and silicates are insoluble except for sodium, potassium, and ammonium, so that's also insoluble. So from this reaction where we just had one precipitate, here we're going to have both of our products are going to create precipitates. So using your general solubility guidelines, you can find out if something is soluble or not. So here we started off with an electrolyte solution because the magnesium chloride was soluble, and when it goes through a reaction, assuming that we have enough to completely react all of our reactants to products, then the resulting solution would not be an electrolyte because both products are insoluble. All right, so we're talking about solubility, general solubility. In terms of general solubility, we looked at having it being unsaturated, saturated, or supersaturated. Okay, but we can talk about specific solubility, and that's molarity. And we can numerically find out just how concentrated a solution is. The symbol for molarity is capital M. Okay, we can't use a lowercase m because that means meters, and we're not talking about meters, so it has to be the capital M for molarity. And the formula for that is moles divided by liters. And that's if we're solving for molarity. If we're going to solve for moles, then we'd have to rearrange this equation, and that's using algebra. We would just multiply both sides by liters, and we would isolate moles on the equal sign, so that would be molarity times liters. And we can also get a third equation, which is liters is equal to moles divided by molarity. Now, you will be given this one on a test, but the others you would have to come up with. So let's work a problem using this. So we have a problem of 0.5 moles of Ki in 0.25 liters. What is the molarity? Well, GSP. What's your givens? 0.5 moles in 0.25 liters. What are you solving for? Molarity. Well, your plan is always going to start off with your equation. Molarity is equal to moles over liters. And since we're solving for molarity, we don't have to rearrange that. So now 0.05 moles divided by 0.25 liters is going to give you a 2 molar solution. So this tells us exactly what the concentration is, 2 molar. Okay, another problem would be find the mass of sodium hydroxide needed to make 250 milliliters of a 0.27 molar solution. Okay, so GSP, what's our givens? 250 milliliters in 0.27 molar solution. And it also gives us the molar mass of sodium hydroxide. Okay, so what are we solving for? We're solving for mass. Okay, so we go ahead and, for our plan, we write down molarity is equal to moles per liter, but we're solving for mass. So we have to look at what we're given, and we have to look at our equation and find out which one of those variables that we can solve for that will eventually lead us to mass. And if we remember about our moles, we can change moles to grams. So we're going to solve for moles. Okay, and moles is going to be molarity times liters. Well, so we have our equation, now we plug in. So we use the 0.27 molarity, and when you're plugging in for the liters, well, we're given 250 milliliters. When we plug this into our equation, we have to convert that to liters, and the way we do that is by dividing by 1,000 milliliters. There's 1,000 milliliters in a liter. So that gives us 0.25 liters. We do the math, we're going to get 0.07 moles. So now we need to convert those moles to grams because it's asking what is the mass. We're solving for mass. So we take our given, we put it over 1, then we put our molar mass of sodium hydroxide here, making sure that moles is opposite moles, so that it can cross cancel. Okay, then we're left with the unit grams, and when we do our multiplication we see that it's 2.8 grams. So we dissolve 2.8 grams of sodium hydroxide into 250 milliliters of a solution, the liquid water, and we're going to get a 0.27 molar solution. Okay, now let's talk about dilution. Well, we have our solutions that we've made, but say we have a solution already. We don't need to make the solution. We have a solution that's made, but we don't need it as concentrated as the original solution is. We need a weaker solution. Well, the formula for dilution is M sub 1 V sub 1 is equal to M sub 2 V sub 2. So what is a dilution? Well, a dilution is decreasing the concentration of a solution, or, basically just watering it down. Okay, you've heard the term watering it down. That's making a dilution. And if we look at this picture here, we can see we start off with a very concentrated solution, and as we water it down or add water to it, it changes the concentration until finally we have a very low concentration of red in this container. So that's looking at a picture what dilution means. Okay, and anytime we talk about dilution, we have an original concentration or a concentration we start with now. We're going to label those with the ones. That's what these ones are. The concentration we have now and the volume we have now. And any future solution is going to be labeled with the 2's. So you have to keep that in mind. And one strategy that I have as I'm reading a problem is I'm looking for present tense and a future tense, or a present tense and a past tense, what we started with and what we end up now. So let's work a problem. Well, we have to make 300 milliliters of a 4 molar solution of sodium chloride. So let's look at that. We have to make. So that's a future tense. So we're going to label those with the 2's. And we have right now a 5 molar solution. So we're going to label this with the 1's. So let's go ahead and do our GSP. The 300 milliliters is the V2 because that's what we have to make in the future. So we're going to label that with the 2, V2. It's a volume, milliliters, of a 4 molar solution. So we're going to label that with M2, molar solution. We have a 5 molar solution, so label that with M1. So how do we do that? Well, what's missing? What are we solving for? Well, the variable that's missing here in our equation is the V1. So our plan, we're going to start off with the original equation. Now we need to rearrange this so that we're solving for V1. So algebraically, we're going to divide both sides by M1. And when we do that, the M1s are going to cancel here and leave V1 is equal to M2 V2 over M1. Okay, so now substitute your numbers in. M2, we're going to substitute our M2 right here. Okay, V2, we're going to substitute in our V2, but it has to be in liters, so that's a 0.3 liters. And M1, substitute in what you labeled M1, which is 5 molar. When we do our math for this, we can see that's 0.24 liters. Well, the question was, how do we do this dilution? Well, we have to keep in mind that our ending volume is going to be 300 milliliters. Now, this is 240 milliliters is what we're going to start with. But our ending volume is 300 milliliters. So what we're going to do is take a container. We're going to pour 240 milliliters in this container. But the ending volume needs to be 300 milliliters, so how much water are you going to add? Well, we subtract that and we see the difference is 60 milliliters. So we have to start with the 240 milliliters of our 5 molar solution, and then we're going to add water to bring the volume up to 300 because that's our ending volume. Now, as we add the 60 milliliters of water, this 5 molar solution is being diluted down to a 4 molar solution. So we have to add 60 milliliters of water to dilute it enough to be a 4 molar solution. Now I get the question all the time, how does this apply to real life? How are we ever going to use this in real life? Well, one application of this is swimming pool chemistry. So if you ever in the future grow up and you have to have your pool where you are responsible for taking care of it, you're going to need to know a little chemistry to do that. Sometimes the pH of your pool gets off. The pH of your pool should be around 7. But if it gets off a little bit, sometimes you have to add muriatic acid to the pool to adjust the pH. So let's say that you have to add a gallon of muriatic acid to your pool to adjust the pH. Well, this muriatic acid is very concentrated muriatic acid, and we can't pour straight muriatic acid from a jug into our pool because it's so concentrated. Concentrated muriatic acid will dissolve concrete. So if you pour it straight into your pool, you could damage the grout that's around your tiles, or you could actually damage the gunite surface, the concrete surface of your pool. So it's recommended that you dilute the solution down to at least a 3 molar solution before you pour it in your pool. Okay, so let's look up the MSDS, the Material Safety Data Sheet for the muriatic acid. Now, what's important to know on this MSDS? Well, we need to know that in this jug of muriatic acid, it's only 31.45% acid, and it's also, muriatic acid is also hydrochloric acid. Okay, and it's also, the molecular weight of muriatic acid is 36.46 grams per mole. And we also need to know the density. Okay, the density of muriatic acid is 1.16 grams per milliliter. And we talked about density in the very beginning of the year. So let's go ahead and write down our givens. It's 31.45% hydrochloric acid. The molar mass is 36.46 grams per mole, and the density is 1.16 grams per milliliter. So what are we solving for? It needs to be a 3 molar concentration. So we know we have to dilute it because it's very concentrated right now. So we're looking for the volume that we need to have. It's not 1 gallon. 1 gallon is concentrated. So we need to know the new volume. How much water do we have to add to this to bring the concentration down to 3 molar? Well, we also don't know the beginning molarity because the MSDS doesn't tell us exactly how concentrated that is, but we can figure it out from the givens that we have. So we don't know the ending volume and we don't know the beginning molarity, but we have enough data that we can figure this out. So what we do is assume that we have 1 liter of our beginning acid, and you'll see in a minute why I picked 1 liter. Okay, and we're going to convert this to moles. Okay, if we take anything to moles, we can go almost anywhere once we convert it to moles. Well, this is where our density comes in. We're going to use, instead of a liter, 1,000 milliliters because the density is 1.16 grams per milliliter. So we're going to put that in our conversion here because we're going to get rid of milliliters and take it to grams. Once we take it to grams, we can take it to moles because we know the molar mass is 36.46 grams per mole. So we set this up in our conversion. Milliliters cancels and grams cancels. And when we do the math here, we see that we have a 32.09 moles. Okay, but this is only 31% hydrochloric acid. So this is where percent composition comes in that we talked about a few weeks ago. So we take our 32.09 moles and we take 31.45% of that. We have to move our decimal over to change this from a percent to a decimal. And we're going to get a 10.09 moles of hydrochloric acid that are in this gallon. Well, now that we have moles, we can get molarity because we know that molarity concentration is moles per liter. So this is why we use the liter here. So we have 10.09 moles in 1 liter of a solution. That's going to give us a 10.09 molar concentration of hydrochloric acid. So this muriatic acid, hydrochloric acid here is 10.09 molar. And that is very, very concentrated. This is a very dangerous acid. This acid will melt concrete. If you pour it on your concrete driveway, it will melt concrete. So it's very dangerous. We want to make sure we take all of safety precautions in handling this acid, wearing gloves, wearing long pants, covering our feet, not wearing flip-flops while you're doing pool chemistry, doing the acid, because this will definitely cause major, major burns. All right, so we're starting with a 10 molar solution. Now we know our M1. So this is very simple now. We're just going to solve for our V2. So we take V2 is equal to M1 V1 over M2. Now we're going to substitute in what we know. It's a 10 molar solution. We have 1 gallon of this, and we need to make it a 3 molar solution. So when we do the math here, we see that we're going to have a final volume of 3.36 gallons. But we have to remember we're starting off with 1 gallon already of the acid. Our final volume needs to be 3. So we're going to subtract that 1 gallon and have 2.36 gallons of water that we're going to have to bring this to a 3 molar concentration. So what I'm going to do is take one of my empty chlorine tablet buckets. They come in 5-gallon buckets for chlorine tablets. And I have those handy. I keep those. I don't throw them away because I know that I'm going to have to do this in the future. Rinse it out really, really well so that you don't have any of the chlorine residue in there that's going to react with the hydrogen chloride and make it more concentrated, because once we add water, then we're going to get more of the HCl. Okay, and the thing about acid is you add acid to water, A to W. And the way I remember that is A and W root beer, A and W, you add acid to water. That's very important. If you do it the other way, then it could cause the water, if you have your acid and you pour water on top of it, it could cause the water to pop and it could pop up onto your skin, which is not good. So I'm going to put 2.36 gallons of water in a bucket, and then I'm going to add my gallon of water to that, gallon of acid to that, to bring the total volume up to 3.36. That's going to be a 3 molar concentration. And now I can safely pour that into my pool without fear of it dissolving the grout between my tile. Okay, so this looks very complicated, and it is really complicated. And that's why sometimes people pay other people to take care of their pool chemistry for them. So if you know this, you don't have to pay somebody. So you can either be the one who pays to have somebody do this, or if you know this, you can be the one that's getting paid to do this. So pay or be paid? That's the question.